Welcome back again, everybody. We're moving forward to lessons 14 and 15, where we'll be solving exponential equations using graphs and logarithms to solve problems. Our learning targets for lesson 14 are to say that we can solve exponential equations using logarithms. We can solve exponential equations using logs or by graphing. All right, so first task is to solve an exponential equation. Basically identifying the steps of what somebody else did. So Lynn wrote the following. She solved for this variable a, which happens to be in the exponent, using this process right here. Your job is to decide, is her solution valid, and be prepared to explain what she did in each step. So try to decide, first, what did she do to get from this step to this step? We'll call that step 1. What did she do to get from this expression or equation to this equation? We'll call that step 2. And third, what did she do to get from the third equation to the fourth equation? We'll call that step 3. See if you can write that down, pause the video for a second, and try to explain what she did in each step. All right, coming back together. First step. To me, what looks like happened is I saw there was multiplication of 5 here. And now we have 18. A quick check and you'll see that 90 divided by 5 is 18. The 5 is gone on the left side, meaning they had to have divided by 5. First step, Lynn divided both sides of the equation by 5. So she basically took 5 times 3 to the a power, or e to the 3a power, 5 times e to the 3a power equals 90, and divided both sides of the equation by 5. So she did in step 1, it looks like. In step 2, I notice that I no longer have the base e, but now we have on the right side a logarithm base e. So it looks like to go from the second equation to the third equation, she just rewrote this in logarithm or logarithmic form. So step 2, Lynn rewrote the equation from exponential to logarithmic form. So she knew that if she had something like e to the 3a equals 18, well, as a logarithm, that's the same thing as just saying that 3a, the exponent, is equal to the logarithm of the base, which was e, of 18. So this is answering that question, to what exponent would we raise the base e to get 18? Well, the exponent in this case is 3a. But we don't know what a is. Until lastly, again, this 3 is gone now on the left side, and it's being divided now on the right side. So to do that, looks like in step 3, Lynn divided both sides by 3. just similarly to what she did in step 1. And divided both sides by 3. So yes, it looks like her solution is valid. So that brings us to a new definition. What we have here, this logarithm to the base e, that's kind of a weird expression. We just learned about this number e, but when we have a logarithm of it, we have special notation. We call this the natural logarithm, because e corresponded to natural growth. So the logarithm of an exponential expression with base e we'll write as ln. So this is natural log. It's kind of backwards. It's like logarithm natural, ln. It means that the natural log of x, ln x, is the same thing as log base e of x. So we need to understand that these two things, they're the same thing. But when we have a base e, we don't like to write log base e. For some reason, math people a long time ago decided we didn't want to do that. So what's really important is that if we have an expression like the natural log of x is equal to y, this answers that same question we've been working with logarithms. The exponent to which we raise a base e, because now that's what we're working with, this base e, to get this x is y. So the natural log of x equals y, well, that's basically the same thing as in exponential form, e to the y power, that's the exponent, y, to get x. To what exponent when we raise the base e to get x? So let's give this a shot with converting between forms. We'll complete this table with equivalent equations. The first row is completed for you. So we have e to the 0 power equals 1. That was rewritten as the natural logarithm of 1 equals 0. So I want you to give it a shot at completing this table. So go ahead, pause the video and try that on your own. All right, coming back together. This first one, e to the first power equals e. We want to write that in logarithmic form. So basically, we want to know the exponent to which we would raise a base e is 1 to get e. So, as a logarithm, we would normally use something like log base, well, the base is e, but like we decided, we don't like this expression, so we'll just use ln instead, basically the same thing. ln of, well, we want to get e equals 1. So this is asking us again, the exponent to which we raise a base e to get e is 1, just like we saw in the exponential form over here. Similar idea here, you should have had the natural log of 1 over e is negative 1, because the exponent to which we raise a base e to get 1 over e is negative 1, according to what we see here. This time we have it in logarithmic form. Natural log of 1 over e squared equals negative 2. So the exponent to which we raise a base e is negative 2 to get 1 over e squared. And this is true because we know that When we have negative exponents, we just flip the fraction and the exponent becomes positive. And lastly, same idea with a variable in here. If we have e to the x equals 10, well, as a logarithm, it's the natural log because it's a base e exponential. To get 10, to what exponent will we raise a base e to get 10? Well, we don't know it yet. It's just x. So in logarithmic form, we can write that expression like this. There's our completed table. All right, the primary purpose of logarithms is to help us solve exponential equations. So we want to solve each of these by expressing the solution using natural log notation. Then we'll find the approximate value of the solution using the natural log button on a calculator. Then we'll round our answer to the nearest 1,000. So 3 decimal places. All right, so in this case, we have e to the m equals 20. Before, I wouldn't know what m is. I'd have to guess and check and see if I can come up with a value close enough to make our answer 20. But now that we know logarithms, we could rewrite this in logarithmic form and then just use the calculator to see what that logarithm equals. So in logarithmic form, this is saying the exponent to which we raise the space e is m, and that will get us 20. So as a logarithm, m, the exponent, should equal the natural log, because it's a base e, of 20. All right, so what's cool now is we have this in logarithmic form. Calculators can tell us exactly what that should be. So let's go to Desmos. Calculator actually has a logarithm button. Desmos, it's in the miscellaneous functions tab. And there it is, ln, the natural logarithm. We want to know the natural logarithm of 20. Oops, not 220. Is 2.9957. So rounded, it's 2.996 to the thousandths place. So m is approximately 2.996. And that answers our question. To check it, this logarithm is really saying to what exponent do we raise base e to get 20? Well, check. Will it be 2.996? E to the 2.996 power in a calculator. Your calculator knows what e is. E to the 2.996 power is really, really close to 20, 20.005. So yes, this checks. It's about 20. All right, so give that same process a shot over here on B and C. All right, sharing the answer with you. Where is it? Right here. So I did this already, B and C. We should have got for B, N should have been 3.401, and for C, P should have been 2.015, and you could have checked your answers. All right, there's page 1. Test 3. I'm going to give you a shot to actually go through and solve a bunch of exponential equations using logarithms. This time we'll do it without using a calculator. So we'll just leave our answers. It's actually expected that some of the solutions will still be expressed using log notation. So you leave your answers in log form without calculating what the logarithm actually equals approximately. Okay, so be prepared to explain your reasoning and everything. All right, for the first one, some of these cases are actually going to be simpler than others. What we could do is just rewrite this expression, this exponential, in logarithmic form. X equals log base 10 of 10,000 is how that would be written in logarithmic form. Then you'd have to use a calculator to figure out what that is, but you could probably actually see what that is already. I should see that this is 3 because I know that 10 to the 4th power, this is 4. 10 to the 4th power is 10,000. So in cases where we actually can write this as a base 10 exponential, might be a little bit easier. Or we could just take 10 to the x power, try to solve this without using a logarithm. I know that 10,000 is 10 to the 4th power. And right away we can see our answer. X is equal to 4. X would have to be 4 to make both sides of the equation true. So, point is, if you can rewrite this with the same base automatically as that exponential side over here, we don't have to use a logarithm. All right, I'm going to skip over to number 6 here as well to show you a case where that doesn't necessarily work. In this one, we're multiplying by 2. Just like Lynn did in the opening example, we can get rid of that 2 because it's being multiplied by applying its inverse, which is division. So if I divide both sides by 2, I should get 10 to the x power equals 400 after we divide both sides by 2. Okay, so now looking at 400, if I were to try to think, does 10 to some power equal 400? 10 to the 2nd power is 100, 10 to the 3rd power is 1000. So no, but I know that this x should end up equaling something between 2 and 3. But to know exactly, we would have to use a logarithm here. So if we write this in logarithmic form, it should be x equals, the base is 10, so log base 10 of 400. And we could use a calculator to find out the approximate answer if we wanted, but it told us to express it using log notation. So we can just leave it in this form. That's our exact answer. All right, your turn. Give it a shot for the remaining 2 through 10. All right, now that you have worked through this, here's the work that I did previously. Take a chance to check your answers. For number 2, we got x equals 2. For number 3, you should have got x equals 1. For number 4, you should have gotten x equals 2. Number 5 was really simple. It stayed in logarithmic form, actually. But it was just one step of rewriting in logarithmic form. Number 6 we did. Number 7, a little bit more complicated. We'd have this full expression right here, x equals log base 10 of 4,000 equals 1, or divided by 1.2. 7 gave us a whole number, x equals 2. 8 involved the natural logarithm because we had a base e. And 10 also involved the natural logarithm. So you should have each of those for task 3. If you have any questions about those, feel free to ask me in tutoring or in office hours. All right, moving on to task 4. What if you were given some sort of a loan, or you have an account, like a savings account, and you put some money in it and you don't touch that money? theoretically, that account should grow based on its interest rate and eventually reach $1 million. So our question is, can we, by depositing money in an account, eventually just retire as a millionaire if we had a really good interest rate on the account? So the expression 1 times e to the 0.06 t models the balance. Key thing is in thousands of dollars of an account t years after the account was opened. So a few things here. This 1, that's our initial value. This is base e, so like we learned in the last lesson, this means it's compounded continuously. So we're adding the interest on top of the interest at every moment of time. And our rate is 0.06. So that's our continuous growth rate. And t is just that time in years. So we want to know, what is the account balance? Take a second, see if you can decide what the account balance is. If you want to pause the video, feel free. Okay, so the account balance, when it was first opened, well, we just got to look at the initial value. So the initial value is 1. Doesn't mean it was $1 in this case, because we're talking in thousands of dollars. So the initial value is 1. This tells us that there was $1,000 when the account was open. All right, now we want to know after 1 year. So we're taking our expression and we're assuming that 1 year passed. So this means that t should equal 1. So now we can just use our expression. In our expression, we should make t equals 1. So wherever we see a t, we'll replace it with 1. 1 times e to the 0.06 times t is 1. All right, let's calculate that. 1 times e, calculator knows what e is, to the 0.06 times 1. Technically, it doesn't matter if we do that because multiplying by 1 is the same thing. But that's exactly what we had, 1.0618. So we'll round it to 1.062 in the thousandths place. So 1.062. So we have 1.062 in thousands of dollars. This just means $1,062 after 1 year. Okay, so how much money did we earn? Well, just by leaving that $1,000 in the 6% interest. Again, 6% interest because that's our continuous growth rate. We ended up with $62 extra in there. Well, let's repeat this process one more time. You can go ahead, try pausing the video and doing it on your own. This time, t should equal 2. We'll take the same expression here, but this time instead of 1, t is 2, which means we can calculate it again. And we get 1.127. So 1.127 thousand is $1,100. $127 after 2 years. All right, for number 2, says Diego says that the expression natural log 5 represents the time in years when the account will have $5,000. Do you agree? Explain your reasoning. Try to do this on your own again, so pause the video and come up with a statement saying whether you agree or not. All right, well, let's think through this. Natural log 5. Our expression is 1 times e to the 0.06 t power. We want to know when this will equal 5,000. Well, 5 is going to represent 5,000 right now because we're talking in thousands. Well, this 1 here doesn't matter. Multiplying by 1 is the same thing. So I'm just going to ignore that 1. We don't really even need it. If you want to just get rid of that 1, feel free. Okay, so then in order to answer this question, we're going to need to use a logarithm. It's base e, so we can write this in logarithmic form with a natural log. So the natural log of 5 on the right side. On the left side, it should just be 0.06t. All right, but we have one more step. In order to isolate t, we're multiplying by 0.06, so let's divide it from both sides. If you divide 0.06 on both sides, we have the natural log of 5 divided by 0.06. So to answer the question, he says that natural log 5 represents the time when the account will have $5,000. But we notice that there's a slight difference. We're dividing by 0.06. So no, we don't agree. Because it should be natural log 5 divided by 0.06. All right, and third, suppose you open the account at the beginning of this year and assume that you deposit no additional money and withdraw nothing from the account. Will the account balance reach $1 million and make you a millionaire by the time you reach retirement? Interesting. So we want to know, when is this expression that we have going to equal 1 million? So just like we did in 2, let's set up that equation. 1 times e to the 0.06 t. But this time, when will it equal 1 million? And we'll decide if that's what we want for retirement. In fact, we're actually not going to put 1 million here because we're talking in thousands still. So how many thousands are in a million? 1 million is 1,000 thousands. If you wrote 1,000 and added it 1,000 times, it would get you a million. So really, if we wrote 1,000 there, that means 1,000 thousands, which is a million. All right, so same thing. 1 times anything is just itself, so don't really need the 1 times. Let's write this as a logarithm. 0.06 t equals base e, so the natural logarithm of 1,000. Divide both sides by 0.06 and we'd have natural logarithm of 1,000 over 0.06. And well, how much time would that be? Calculate it real quick. natural log of 1,000, close the parentheses, divided by 0.06 gives us 115.12. So that means that's the number of years. So it would take 115 years to reach 1 million. So we probably won't retire millionaires. Unless you retire after 115 years. Good luck with that. So maybe it would have been better if we started with more money in our account than $1,000. All right, task 5, a cicada population. Cicada is like a grasshopper type insect here. It looks like that. Population of cicadas is modeled by a function defined by this expression, where W is the number of weeks since the population was first measured. Explain why this equation gives us the number of weeks it takes for the cicada population to double. Well, looking at the expression, we know the initial value is 250. So because the initial value is 250, and if you look at this, it wants to know when will it be 500. We want to know when it will be 500. And 500 is double 250. So which is, we'll say twice as much as 250. Says much. All right, so now how many weeks does it actually take to double? Let's just solve that equation. We'll round it to the nearest tenth. So 500 is equal to 250 times e to the 0.5 w. So that's our continuously compounding interest rate of 0.5 or 50% really. So it's doubling every week. All right, so solve this equation. We can divide both sides by 250. And we get 2. 500 divided by 250 is 2. E to the 0.5 w. Since we have an exponential expression, to solve the exponential, let's write it in logarithmic form. Natural log of 2 is equal to 0.5 w. Last thing, we need to isolate w. So let's just divide both sides by 0.5. Here's our answer in logarithmic form. We want to get it as a decimal answer though. So let's divide the natural logarithm of 2 by 0.5. We get 1.386, or rounding to the nearest tenth, 1.4. So this means that W equals 1.4, which means it would take 1.4 weeks to double. All right, and lastly, below are the graphs of y equals FW and y equals 100,000. Explain why we can use the intersection of the two graphs to estimate when the cicada population will reach 1,000. Well, looking at this graph, this will tell us exactly how many weeks it took to reach that amount, 100,000. You can enter this into Desmos. Getting rid of all these, our expression was 250 times e to the 0.5 w, but we'll use x because Desmos likes the variable x better. We want to know when it's going to equal 1,000. Y equals 1,000 on the y-axis. And if you were to zoom this out so that we could see 1,000 or 100,000, this intersection will tell us the exact amount of time. So why? Because it tells us when the output, or we should say the input, tells us the input that will give us an output of 100,000. So we can solve these graphically as well. All right, and that's the lesson. I'll be available for office hours as well as tutoring on Wednesday if you should have any questions. The assignment will be given with this as well. Hope to see you in my office hours. Let me know if you have questions otherwise. Have a good one.